Okay, so this next section concerns two very important properties. Um, so these are theorems. These are things that can be proven. And I think in the last video I said, well, I wasn't going to prove the extreme value theorem, and I said it's in the book if you want to read it, great. I think I am going to prove this one here. So we're going to look at the proof. Now, we're not going to do a lot of these, but for those of you that want to go on to mathematics, just realize that not all math is just, calculate derivatives and stuff. In fact, calculating derivatives is, well, in my opinion, kind of the boring part. It's very mechanical, right? You have a function, you apply the rules, you take the derivative, right? Not the most interesting thing to do, especially once you get used to it, right? Once you understand the rules and can use the product rule, the chain rule, the quotient rule, then, then it's just getting more and more complicated functions, and then you just have, then it's just tedious, right? So, for now, hopefully you're finding calculating derivatives kind of fun. At least I know I did when I first took calculus, but most of sort of the higher levels of mathematics actually are looking at properties and theorems and how to actually show that they're true. And so a proof is just a demonstration that this will work in all cases, right? So we're not looking at specific examples here. We want to show that this property is true in all cases. Okay, so that's called a proof, right? And I think this is our first one. I don't think we proved a whole lot in this class so far. And to be fair, we're not going to prove a lot of stuff in the future because it's a more advanced thing, right? So if you go on to a course in analysis, which is a branch of mathematics, then I would say most of what you do are proving things there, right? So for you engineers out there, you're probably not going to prove a lot of things, although you never know. It might come in handy in some cases. All right, so before we can prove this, let's read the theorem here. It's called Rolle's theorem. Probably the first one who proved it, although I don't know that for sure. In fact, these theorems are sometimes named after people that had very little to do with the actual theorem, coming up with the theorem or even proving it in some cases, but I have no idea. So Rolle's theorem states the following. We have a function f, right, and it's continuous on a closed interval from a to b. And it's also differentiable, so the derivative will exist everywhere between a and b, right, on the open interval from a to b. And one more condition, right, f of a is equal to f of b, right? So the values at the endpoints are going to be equal. And now we can sort of fill in the picture here, right? So in order to prove it, we might want to take a look at a graph. So here we have a and here we have b. So we're only going to be restricted to this interval between a and b, right? So let's graph a function where f of a, so that's here, has to equal f of b. So what can happen in between? Well, you can have crazy stuff like vertical asymptotes, but it's got to be continuous. So that rules out asymptotes, right? So you can't have a gap like this in it, because that's not continuous either. So, it might look like this. Okay, so that's continuous. However, remember, it also has to be differentiable. Differentiable means you have to have a tangent line. And at this point here, we don't have a tangent line. So it's got to be more than just continuous. It has to be smooth. So let's draw a nice smooth function between a and b, right? And in fact, let's call the y-coordinate here, let's call it d, right? So that's the same as f of a and f of b. They're both equal to d, right? They have to be equal. That's one of the conditions. So the conclusion is as follows, right? The conclusion says that there has to be a number c between a and b such that the derivative at c is 0. So if the derivative is 0, well, we know it's a critical number, right? But moreover, that you have a horizontal tangent line. So do we see a horizontal tangent line here? Sure, right about here, that would occur at that value of c. So let's call it c1. Do we see another one? Sure, down here. So that would be c2. So, right. So notice in the theorem it says there's at least one number c. There could be more than one. In this case, it looks like there's two. Right? But you can have 3 or 4 or 5, but you have to have at least one. Okay. So what the point is, when you draw a differentiable function from a to b, right, like this, so that the y-coordinates are the same at the endpoints, right? There has to be a point somewhere in between where you have a horizontal tangent line. And that'll be at c, and again, you can think of c as a critical number here. Okay, so that's the idea. That's what has to happen. I didn't want to erase it. This is your c, and then this is your horizontal tangent line here. Okay, so now I think we can try to prove it. And again, this is something that takes a lot of practice, and it's not something you're going to get good at proving things until you take a good course in algebra, advanced algebra, or I shouldn't say advanced, abstract algebra, or real analysis, or a course in topology. But again, those are a few semesters off, right? So this is just to get you used to the idea, right? So first thing we're going to do is, let me go back. Okay, so let's try that again here. Okay, so let's let d be the y-coordinate of the endpoint, right? So it's f of a and f of b. Okay, so this is kind of complicated. We're going to break it down into 3 cases. So the first case, case 1, goes like this, right? Suppose that f of x is equal to d as well for some x between a and b, right? Including possibly at a and b. Right? If that's the case, and suppose that the derivative of the function at x is also 0 there, right? Or in fact, let's suppose that it's true for all x between a and b. Right? So, I'm sorry. I didn't mean this. Okay. I really should start over, but okay, so case 1 says the following, right? Suppose we have a function f of x is equal to d for all x between a and b. So for all x between a and b. What that means is that f of x equals d is just a horizontal line. So that's f of x equals d. But in that case, you can pick any x in between, and the derivative will be 0 there. So, right, so then in that case, all the points in between here are critical numbers. The derivatives will be 0 everywhere. Okay, so of course there's going to be at least one number c. Take your pick. Any one of these c's here will have the derivative equal 0. Right? So that's kind of boring, right? But that could happen. In other words, if the function is a horizontal line, then its derivative is 0 everywhere, not just at the endpoints, right? Okay. Now we get to the more interesting case, case 2. So in this case, we're going to assume that f of x is going to be bigger than d, right, for some x between a and b. So for some x between a and b, we're going to assume that f of x is bigger than d, right? So that picture is more of the original, so let me erase this and we'll come back to it. Okay, so in this case, what we're going to have is this. So here's my A, here's my B, and so in this case, we know the function, here's my D, is not just horizontal everywhere. That's case 1. But instead, for some x, there's going to be oh no, f of x will be bigger than d. Yeah, so for some x in between, it's going to be bigger, right? So it's got to look something like this. Okay. All right. So notice what has to happen here. This is a continuous function, right? That's one of the conditions. It's a continuous function on a closed and bounded interval, right? We're assuming that x is between a and b, including a and b here. I skipped over a little bit. So yeah, this is a closed and bounded interval, and f is continuous. So if you remember, the extreme value theorem says that you have to have a maximum between a and b. And when you look at the picture, of course there's a maximum right about here. Let's call that c, right? And so for f of c here, f of c will be the highest point. It'll be the maximum, a relative maximum. Okay, so what that tells you is that if you have a relative maximum and the tangent line is horizontal here, we know that because it's differentiable, right? So coming to a corner like this, we ruled that out earlier, saying that it's not differentiable. So being differentiable, that means that f prime of c has to equal 0. Oh, 0. Sorry, this little stylus is not working very well, but I think I got my point, right? F prime of c has to equal 0 there, right? But notice that's the conclusion. That we have to show that f prime of c is equal to 0 for some c in between a and b, right? On a and b or in between a and b. And we did that, right? So that's case 2. And finally, case 3 is really just the opposite of this. Suppose that the function f of x is less than d. It's a funny looking d, right? For some x between a and b, right? So now the picture is reversed. So this is my a, this is my b, and if f of x is less than d, this is the d here, then it looks something like this. Well, so now your tangent line will still be horizontal here, right? Say it's c. But now it's a relative minimum instead of a relative maximum. But either way, the derivative still has to be 0 there. Right? The derivative has to be 0 because the tangent line is horizontal, right? The slope is 0. And so that does it as well. So now, right, f of x could be equal to d, bigger than d, or less than d. So whether d is bigger or smaller than f of x doesn't matter. You're going to get this conclusion here. We have to conclude that there is such a c where the derivative equals 0. Okay. The theorem doesn't tell you where it is. It just tells you that there has to be one. There has to be a c, a critical number, where the derivative equals 0. Not where the derivative does not exist, right? It's differentiable. So the derivative will exist everywhere from a to b. Okay, so that's the proof, right? So hopefully you believe that. If not, doesn't matter, because we're going to figure out how to calculate the c later. Before we do that, we're going to go on to another property called the mean value theorem. And here it is. This is the mean value theorem. Okay? And it says the following, right? We have a continuous function f, right? So f is continuous. F is continuous on the closed interval and differentiable on the open interval. So just like in Rolle's theorem. But notice there is no condition here that f of a has to equal f of b. Right? That may be true, but it doesn't have to be true here. Okay? So, there is at least one number c between a and b such that the derivative of f at c doesn't have to equal 0 here. What it has to equal is f of b minus f of a, all divided by b minus a. And that may look familiar, right? That's like the difference quotients, right? So let's draw a picture here and we'll see what's going on. Okay, so let's say this is my A and this is my B. Right? Now f of A can be down here. F of B can be way up here. They don't have to be equal anymore. And let's draw a nice continuous function from point A to point B. So what could that look like? It could look like this. Right? So that's my f. Right? Nice continuous function and differentiable too, right? So again, you don't want to draw one that comes to a corner like this because then it's not differentiable there. Okay. So let's start with the right-hand side. What is this thing here? F of b minus f of a over b minus a. Well, this should remind you of y2 minus y1 over x2 minus x1. Right? In this case, I'm using a instead of x1 and b instead of x2, and f of a instead of y1 and f of b instead of y2. But yeah, this is just rise over run, right? This is the slope of a secant line passing through point A and point B. Okay. And the line keeps going, of course, in both directions, but the slope, right, is just the rise over the run. So, right, so this is the rise, this is the run. Oh, it looks almost like, 1 over 1, right? It could, so the slope could be 1 here, but it doesn't have to be. Okay, so that's the slope of this line here, right? So we'll just call this m, right? In this case, it looks like it's 1, maybe a little less than 1, I don't know, but 0.9 or something. But it's a slope, it's a number. Now, let's look at the left-hand side, f prime of c. So where's c? Well, remember, f prime of c is the slope of the tangent line at c, and that tangent line has to have the same slope as this red line. So where's that c? It's not going to be here, because up here, the tangent line has slope 0. This red line the slope is clearly not 0, right? It's not a horizontal line. So where would my c be here? Might be somewhere around here, right? So if I draw a tangent line at that point, that looks pretty close, right? That looks pretty close to the slope of the red line, right? And the two lines are parallel. Parallel lines, remember, have the same slope. So my c then would be, right about halfway in between. And who knows, it could be exactly halfway in between. But it doesn't have to be exactly in between. It's just somewhere between A and B, right? So that's what the mean value theorem says. The mean value theorem says that there has to be a c such that the tangent line at that point will have the same slope, these will be equal, as the secant line passing through point A and point B. In other words, the slope of the red line has to be the same as the slope of the blue line, which is the f prime of c, right? So yeah, this m here is going to be the derivative of f at c, because that's the slope of the tangent line at c, right? Okay, so that's what the mean value theorem says. Do you buy it? Well, again, from the picture it's pretty clear, but is it clear for every case? Is it clear for any function, not just the one that I drew? Right. So in other words, should we prove it? What? Okay, no, I'm not going to prove this one. We proved Rolle's theorem, and to be fair, that one's actually harder. I think if you look at the proof of this in the book, it's actually a little bit easier because it relies on Rolle's theorem. So we had to do Rolle's theorem first in order to do this one, at least in order to prove this one. But we're not going to prove it. Right. The trick, of course, is to look at a function, and we're basically going to tilt this so that this slope becomes 0, right? So we're going to take a new function, We're going to call it y is equal to f of b minus f of a over b minus a, all times x, all times x minus a, plus f of a. So this new function, we can call that g of x if you like. You can show that g of x will then look like this. It'll satisfy Rolle's theorem. So then you use Rolle's theorem on g of x, and that would prove the mean value theorem. So that's just a brief sketch, right? If you didn't follow that, don't worry about it. Right? The point is, I'm never going to ask you to prove anything on a test. At least not in this version of calculus, right? In a more advanced calculus course, you may have to prove things, but not here. Okay, so yeah, so the next thing we'll do is some examples of how can we find the C where this is true. Okay, so we'll do that as an example here. Okay, here's our first example. It says to determine if the conditions for Rolle's theorem are valid for this function, f of x, and maybe I should copy that down because, again, it's kind of small. So we have f of x is x times x plus 2 times x minus 4. And, you know, if you want to multiply it out, you should get, let's see, x cubed minus 2x squared minus 8x. You didn't have to do that, but remember, we are going to be taking the derivative in a little bit, and in order to take the derivative of this, you would have to use the product rule twice, actually. So rather than do that, we'll expand this out, and hopefully it'll be easier to take the derivative later. But before we do that, right, so, and this is on the interval, let's make that clear, from -2 to 4. So that's my a and b, right? A is -2, b is 4. Okay. So yeah, so before we take the derivative here, let's see if Rolle's theorem applies. Right, so does Rolle's theorem apply? Well, remember what Rolle's theorem is. I'm going way back up here. We have a continuous function on a closed interval. Well, we know the closed interval, but is it continuous and differentiable? Well, yeah, it's a polynomial, right? Polynomials are, almost by their nature, they are continuous, and we can take their derivative, so they are differentiable. It's a long word, but differentiable. So, yeah, so that part applies. There's one more condition, if we can scroll back for a minute. F of A has to equal f of B, remember that? So is that true here? If I take f of A, what's A here? A was -2, right? So what's f of -2? So I can plug it in here, but notice I can plug it into the factored form. We just get -2 times -2 plus 2 times -2 minus 4. So you just get -2 times 0 times -6, which is indeed 0. Now for Rolle's theorem to apply, I have to find f of b. Remember, b is 4 here, and that has to be 0 as well. They have to be the same. Remember, f of a has to equal f of b. Right? They don't have to be equal to 0, but they have to equal the same number, right? So they can both be equal to 7, let's say. But we know that they're both going to equal 0, and we know that because we get, x is 4 now, right? So 4 times 4 plus 2 is 6, times 4 minus 4 is 0, 4 times 6 times 0 is 0. So yeah, they're both equal to 0. So continuous differentiable and f of a equals f of b, so Rolle's theorem applies, right? Rolle's theorem applies. Okay, so let's apply it. Let's find the c, find the critical number c, right, between -2 and 4, so that f prime of c equals 0. So basically, just find the critical numbers, right, wherever the derivative is equal to 0, and I know that was crazy sloppy, right? So on c, such that the derivative of f at c equals 0. Right. Does not exist. That does not apply here. It's got to equal 0. So now we take the derivative, right? And I'm going to use this version because I'd rather not use the product rule here. So we just get 3x squared minus 4x minus 8. So where does that equal 0? Well, you can use the quadratic formula, or you could try to factor it. So can we factor it? Let's see. We need two numbers that multiply to negative 8. So how about 2 and 4? Which one's negative? Let's see. So this will be 6 minus 4. That'll be positive 2. If we reverse it, we get negative 2. So that doesn't work. So I could do the 4 here and the 2 here. So that'll be 12 minus 2 is 10, or negative 10. That's not going to work. All right, what about 1 and 8? So you get 8 minus 1 is 5, or negative 5. Close, but we need negative 4. This is not looking good. I guess we can't factor it. Maybe it's not factorable. Okay, well, in that case, now we don't have a choice, right? Now we have to use the quadratic formula. B is negative 4, C is negative 8. So by now you know the quadratic formula. Obviously, on a test, you can just look it up. But you should know it. You've done this many, many, many times, right? So plugging in the numbers, we have negative, oh, careful, B is negative 4, so that's going to be a positive 4, plus or minus the square root of B squared, so negative 4 squared, minus 4 times A is 3, and C is negative 8, all divided by 2 times A. Okay, so now just do the arithmetic carefully. We get positive 4 plus or minus the square root of 16 plus 12 times 8, which is 96. Right, all over 2 times 3 is 6. So this is just 4 plus or minus the square root of 112 over 6. Yep, 112 is not a perfect square. So yeah, the factoring was doomed, but it was worth a shot. And usually it will be factored, but they'll be nice numbers. But in this case, not so nice, right? So what are these numbers here? Right, these are your C's, really. We'll come back to that. So the square root of 112, what's 112? Can we simplify that? Yep, I think we get 16 times 7. So we can, sorry about that, we can do square root of 16 times square root of 7 over 6. So that simplifies to 4 plus or minus 4 square root of 7 over 6. And we can divide by 2 here, so we get 2 plus or minus 2 square root of 7 over 3. And let's see, when you use the plus, I think you get that this is approximately 2.43. And if you use the negative, the minus sign, you get negative 1.098. So we'll round to 2 decimal places, negative 1.10. So these are our C's now. And I think they're both between negative 2 and 4. So yeah, there's actually 2 different C's here. There's only guaranteed to be 1, but again, in some cases there could be more than 1. So both of these numbers, the plus and the minus, are your C's here. So C1 is 2 plus 2 root 7 over 3, and then C2 is 2 minus 2 root 7 over 3. And again, one of them, the C2, is approximately negative 1.1, and the C1 is approximately 2.43. but that answers the question. If you plug those numbers into the derivative, you should get 0. Okay. Yep. And again, I think this is a good one because, again, not all of them will be factorable, right? Sometimes you will have to resort to using the quadratic formula, which is why it's a good idea to have that memorized. So that was our first example. Maybe we should do one more. Yep, let me clear this. Okay, example 2. Determine if the conditions for the mean value theorem are valid for this function. And let me write it down. It's just x to the 4th minus 8x. This is not working. Here we go. Okay, f of x is equal to x to the 4th power minus 8x. And the interval is from 0 to 2, right? So again, a is 0 and b is 2. So remember the mean value theorem? Well, if not, I'll remind you. Remember, f has to be continuous, and it is, right? It's a polynomial, binomial, and differentiable, and it is. In fact, we can take the derivative right now pretty easily. We get 4x to the 3rd minus 8. So if the derivative exists everywhere, it's differentiable. And that's it, right? We don't have to worry about f of a equaling f of b. In fact, f of a is, let's see, well, yeah, what's f of a? So f of 0 is 0, and f of b is going to be f of 2. So that'll be 2 to the 4th minus 8 times 2. So this is going to be 16 minus 16. Oh, we get 0. Oops. So this is not only the mean value theorem, this is actually Rolle's theorem as well, because we get the same value for f of a and f of b. Okay, right, they're both equal to 0. So the answer is yes, the mean value theorem applies. Rolle's theorem is a special case. So if Rolle's theorem applies, certainly the mean value theorem also applies. So remember, the condition for or the conclusion of the mean value theorem says the following. I'm just copying that down. And so what is f of b and f of a in this case? Well, they're both equal to 0. So we get 0 divided by 2, which is 0. And again, in general, for the mean value theorem, you might get some other number. It doesn't have to be 0 here, right? But that's the right-hand side. And so for the left-hand side, we're looking for where the derivative equals 0. So yeah, we're looking for the critical numbers again. So if we plug in c, we didn't have to do that here, but if we plug in c, let's solve this equation for c. Add 8 to both sides, and we get 4c cubed equals 8. Let's go up here now. Divide by 4. We get c cubed is equal to 2. So c then, just take the cube root of 2. Remember, this is the cube root, right? There's no plus or minus here. It's not the square root. If you were taking the square root of both sides, you would need a plus or minus, but not in this case. All right, so if that's my c, well, what is this approximately? Just to round it, I think it's 1.26. About 1.26, which is between 0 and 2, right? That has to be the case. Remember, c has to be right between a and b, or in this case, between 0 and 2, and 1.26 certainly qualifies. Right. Right. Yeah. Suppose we got c equals 12, for example. Well, 12 is bigger than 2, so that would not count. That would not be one of those c's here. Right. So there's only one c in this example, and it's the cube root of 2. Okay, let's do one more. Okay, so the next one says to determine if the conditions for the mean value theorem, and again, this might mean Rolle's theorem again, but its mean value theorem is more general, are valid for f of x equals, and let's write the function down here, f of x equals x plus 2 all over x on the interval from -4 to +1. Okay, so mean value theorem, right? First thing, f is continuous on -4, 1. Is it? Well, this is not a polynomial. This is a rational function. And either way you write it, right, if it's x plus 2 over x, right, we could also write this as 1 plus 2 over x. But either way, look what happens at 0. F of 0 is undefined. It's not in the domain, and it's not a whole, right? It's not indeterminate. It's a vertical asymptote, right? So f is definitely not continuous everywhere between -4 and 1, right? 0 is between -4 and 1. So, you know, if the denominator was, say, x minus 3, and then, right, so it would be undefined at 3, but 3 is bigger than 1, so that wouldn't matter. But here, we got x equals 0, and 0 is between 4 and 1, so f is not continuous on this interval. It's not continuous between -4 and 1. Right? It's continuous almost everywhere, but just not at 0. So we cannot conclude that it's continuous everywhere between -4 and 1 because, well, everywhere would include 0, and yeah, it's not continuous at 0. So we're done. Right, it's not continuous. It's also not differentiable at 0. Right? And so is the conclusion true, right? Is there a C here where this is true? Right. Well, if it is, then it's a coincidence. It doesn't have to be, this doesn't have to be true. And I think it's not, right? So let's calculate this. Let's see what happens. Even though there's no guarantee that this will work, right? That this equal sign might not be true here. What is f of 1? F of 1 is 3. And f of -4, so -4 plus 2 is -2. -2 divided by -4 is +1/2. Right? And then 1 plus 4 is 5. So I think we get, let's see, 2.5, right? 2.5 divided by 5, which feels like 1/2 to me. So the right side is 1/2. Now, is the left side equal to 1/2? So f prime of c, is that equal to 1/2 for some c between -4 and 1? Okay, so we didn't take the derivative yet. Let's take the derivative. So here's f of x again, x plus 2 over x. So quotient rule. You can use the quotient rule if you want. I'm not, because remember this is just 1 plus 2 over x, or 1 plus 2 times x to the -1. So to take the derivative, we don't need the quotient rule, we just need the power rule, right? And the sum rule. The derivative of 1 is 0, so this will be 2 times -1 x to the -2, or just -2 over x squared. Okay, so that's the derivative. F prime of x, right? So if I plug in c here, I get -2 over c squared. Does that equal 1/2? Can we solve this equation here? Well, let's try it. It's cross multiply. We get c squared equals -4. So c is plus or minus 2i. And remember, when you get imaginary numbers, cross them out. They're not real numbers. We don't care about those in this class. So the answer is no. This has no solution. Well, no real solution, which is all we care about. Right. So there is no c where f prime of c equals 1/2. So it turns out there is no such c. But, of course, that's not surprising. There was no guarantee because the condition for the mean value theorem that f has to be continuous and differentiable, well, that's not true. So then there's no guarantee that this will even work. And it doesn't. It doesn't here. So fair enough. We didn't have to do that, but we did have to show that f is not continuous and not differentiable. Oops, I should say not continuous and not differentiable between -4 and 1. Okay, so yes, so determine if the conditions, right, the conditions are not valid, so we didn't have to find a C. We tried anyway, but we didn't get anywhere. We didn't get any C's. There are no C's here. Effectively, there's no critical numbers, at least between -4 and 1. And in fact, I don't think there's any critical numbers at all because the derivative is never 0. It's never equal to 0 for any x. The derivative is undefined at 0, right? So the derivative does not exist. Sorry, I keep saying undefined. I mean the derivative does not exist at 0. But remember, that doesn't mean it's a critical number because the original function doesn't exist either. Makes sense? Okay, so that's mean value theorem. Okay, I mean, this is going to be a shorter video anyways, but I want to do one more example, and you may or may not see this in the homework. I think there might be one of these in the homework. In fact, this might be the one, but that's okay. This is not an easy one, right? This is sort of a practical application for the mean value theorem or Rolle's theorem. Yeah, so let me read the question because it is kind of tiny up here. The question says, a bus starts its trip at 9 a.m. So let's write that down, right? So we have a bus and it starts or leaves, I should say, at 9 a.m. Right? And arrives at 12 p.m. At 12 p.m. it reaches its destination. So it arrives at 12 p.m., which is 3 hours later, right? And the destination is 160 miles away. So the bus traveled a distance of 160 miles, right? In 3 hours, right? From 9 to 12 is 3 hours, right? So we have to show the following. We have to show there were at least 2 times right during the trip the bus was going 50 miles per hour. Right. How do we know that for sure? Right? I mean, buses can travel pretty fast now, right? How do we know that it was going 50 miles per hour at all? All right, maybe the fastest it was going was 48 miles per hour. If it doesn't travel on big highways or whatever. Yeah, so we want to show that it was traveling 50 miles per hour. In fact, at least twice. Okay, so here's what we're going to do, right? We have to start giving things names. Let's say S of t is the position function of the bus. Right? So the graph might look something like this. Sorry, it's a little crooked here, but this is supposed to be S of t, right? So let's suppose that 9 a.m., well, let's just call that t equals 0. That's when we'll start our clock. 12 p.m. is 3 hours later, so let's say that's t equals 3. So we're traveling 1, 2, 3 hours, right? We're starting at 0. And let's say our position at 0 is 0. We're starting at our starting point. Might as well call that 0. And then 3 hours later, we traveled how far? 160 miles. And that's up here. Okay. So what happened in between Well, we don't know, right? I mean, presumably the bus started slow, went faster, faster, slowed down, faster, slowed down, right? So this could be the position function. I know it's kind of a weird function, but we really don't know what happens in between. It could look like anything, right? Well, it can't do this, right? You can't have a gap in the position. If you think about it, at this moment, the bus sort of teleported from, say 50 miles, and then 1 instant later, it was 90 miles away. So it traveled 40 miles in 0 time. Buses can't do that. I don't think anything can do that. You can't just, you can't jump around, right? The bus is not going to suddenly over here, and then the next instant it's going to be over here, right? It's got to take some time to get from one place to the other. So what I'm saying is, right, this has to be a continuous function. And we might as well also assume that it's differentiable, right? Unless it slams into a brick wall or something, which would be very bad. It's going to be a nice differentiable, smooth function, right? So it's going to be some sort of a nice smooth function here. Might look like this, right? Okay. But we also want its velocity. Remember, how to get the velocity is take the derivative of the position. So this will be the velocity function. And I think one thing is for sure, if we're graphing the velocity function here, right, so this is still 1, 2, 3 hours later. And this is, let's say, well, actually, right, this is the velocity now, so we're not looking for distance. I think we can assume that when people get on the bus, it's not moving, right? So its initial velocity has to be 0. So that's 0 here. And what happens after 3 hours? Well, the bus reaches its destination, and then people get off the bus. Well, again, the bus has to be stopped. You're not going to get off a moving bus. I would hope not. So, yeah, so after 3 hours, you get to your destination, it stops, right? So the velocity at 3 is also 0. And so what happens in between? Well, the bus obviously has to move a little bit, so it has to have some velocity, right? And then it might reach up here, and then it's got to slow down again. It might slow down, and then eventually it'll reach 0. So this might be the velocity function of the bus. Okay. So, does this condition look familiar? Remember, f of a equals f of b? Or in this case, v of 0 equals v of 3. So, right, so my a is 0 and my b is 3 here. Starting point is 0, stopping point is 3. Right, and these are both equal to 0, although they don't have to be equal to 0, they just have to be the same number. But obviously the number is 0, because you're starting from rest and you're gonna stop when you reach your destination, right? So, so that's that. Yeah, so Rolle's theorem, right? And we're assuming that v is also continuous and differentiable. It doesn't really make sense if you have a gap or a jump in the velocity either. Right? The bus is not going to go 10 miles an hour and then all of a sudden it's going 90 miles an hour. It's going to take some time to speed up to that, right? So, yeah, so continuous differentiable. So Rolle's theorem applies. And what does Rolle's theorem say? It says that if these conditions apply, there is a value of c, right, between 0 and 3, right, at which, right, the derivative of v, do I want the, yeah, I want the derivative of v at c has to equal 0. Okay. So there has to be a C where the tangent line is horizontal. And that might happen more than once, but we know it happens at least once here. Right? At least once here. And in fact, right, this is going to equal the average velocity. Right? What was the average velocity of the bus? Well, it traveled 160 miles in 3 hours. So what is that? 53 1/3 miles per hour. Right, so this was average velocity. This is average velocity, right? And so since that was the average speed, oh, I think we are using the mean value theorem here, after all. We're using this top picture. Maybe I should do a green line here from 0 to this point. So the slope of this line is 53 1/3. Right? And so there has to be, yeah, so that's the same C here. Right? It looks like C equals 2, but it doesn't have to be. It could be anywhere in between. Right? Where the velocity is 53 1/3. So remember, the question was to show that the bus was going 50 miles per hour. Well, that's slightly less than 53, right? So that might be right here. So if this red line is v is equal to 50, let's draw that line. And does that cross the velocity graph anywhere? Well, sure, it crosses it here and again here, twice. Right? So there were 2 moments, C1 and C2. These are times, right? Could be, 1.2 hours later or 2.5 hours later. But there are 2 moments in time when the velocity was exactly 50 miles per hour. Has to be the case, right? If the bus was going 53 miles per hour at some point, in order to get to 53, it has to get through 50 first. Right? It doesn't make sense to go 25 miles an hour and then suddenly you're going 53 miles per hour. You have to speed up. And when you speed up, you're going to pass 50 miles per hour. So, right, so yeah, in other words, v of t equals 50, right? This equation has at least 2 solutions. 2 solutions. Sorry, that's better. I can't spell. At least 2 solutions. Right. So that's by Rolle's theorem, or in this picture here, it would look something like this, but that's the mean value theorem. Either way, either graph shows that there has to be, this is m is equal to 50 here. There has to be at least 2 times where the instantaneous velocity was 50 miles per hour. I hope that helps. Again, kind of a weird question, and there's other questions like this. Right, so again, the question wasn't at what time was the bus traveling at 50 miles per hour. We don't know what time. All we know is that there has to be a time, sometime between 9 a.m. and 12 p.m., where the velocity was 50 miles per hour. In fact, there has to be 2 such times, at least 2. Make sense? Okay, so that's the power of Rolle's theorem and the mean value theorem. It can demonstrate that, in this situation, the bus had to have been traveling this fast. There's no way around it, right? Okay. Again, somewhat of an abstract question, but right. If you use the mean value theorem here, right, or Rolle's, I think it's Rolle's theorem in this case, but it could be either. Then that guarantees that the velocity has to be 50 miles per hour, right? Oh, this statement here where I wrote v prime of c, that just means the acceleration is 0. And that just means that at some point the velocity maxed out, right? And it could have happened at 53 miles per hour, but it could have happened faster than that. I mean, the bus was probably traveling faster than 53 miles per hour at some point. We just don't know when. All right, well, I hope that helps. But most of the problems will be like this, right? Find the C where the mean value theorem applies or where Rolle's theorem applies.